Okay, so we'll start the next module, that is the electronic spectra of diatomic molecule. Electronic spectra of atomic. So here in the uh, last module we have discussed about the Raman scattering and Raman spectra associated with the different samples, and before that we have discussed about the microwave spectroscopy and as well as the IR spectroscopy. So all these things will is associated with, for example, in the case of the microwave spectroscopy, it is associated with the rotation of the molecule, and the IR spectroscopy, which is associated with the vibration of the molecule, okay? And the Raman spectroscopy, which is associated with the scattering by the molecule. So all these processes also need some basic requirement. For example, in the case of microwave spectroscopy, it requires a permanent dipole moment in the molecule. Similarly, for the IR spectroscopy, which needs also needs a change in dipole moment in the molecule, the change in moment. Then, in the case of Raman scattering, also we have a change in polarizability or polarization of the molecule. Okay? And this one, electronic spectra of the molecule, if you consider, this is associated with electronic transition. So it does not having such kind of requirement. And if you are having an electronic transition which is happening in the molecule, then associated with that we will be having the all other transitions. I mean the vibration as well as the rotational spectrum. So with the electronic transition, we also have vibrational transition as well as the rotational transition. So in an electronic level, so in an electronic level, we consider large number of vibrational levels exist along with that large number of rotational levels in each of those vibrations. So we already discussed that in a vibrational transition there will be large number of rotational transitions, and we discussed about those rotation and vibration, all those things. If you are if molecule rotating like this, then within that rotation we will be having large number of vibration transition which will be happening. So in a single vibrational level, there will be large number of rotational levels. Is also happening. So if you consider a vibration, for example, molecule, say this if it is rotating like this. Okay. So in a single vibration, let's say if it is a stretching mode like this. Okay. So in a single vibration, it will be having large number of rotation which will complete. Which means that in a single vibrational energy level, there will be large number of rotational energy levels associated with that. And we already plotted those things in the when we discussed about the in an electronic level, energy level, we'll be having large number of vibrational level, and in all those vibrational level, we'll be having large number of rotational. Okay. So this electronic energy level will be having the highest energy difference. So that transitions, this electronic transition will be giving highest energy. Okay. And then vibrational and then rotational. So that is the first point in an electronic level. I think you can just read that from textbook. So if you consider an electronic energy level, and this consists of large number of within a electronic level, we have large number of vibrational level. And in all these vibrational levels, we have large number of rotational. So if you consider that as an energy band diagram, suppose you're considering energy like this. Okay, so if you're having this as your the electronic transition levels or electronic energy level differences, so within this energy, so for example, if you consider this energy, within this transition, we will be having large number of vibrational as well as rotational transition will happen. Okay. So anyway, we'll discuss it. So within a single electronic level, we'll be having a number of vibration energy level, and in each of that vibration level will be large number of vibration. Okay, so for this during an electronic transition, okay, vibration and rotational energy changes can also occur, and these vibrational changes during this electronic transition that is happening in molecule, which is called as vibrational core structure, and the rotational changes which is happening because of this electronic transition is called as rotational transition. Okay. So what is this means? In a single electronic level, we have a large number of vibrational and rotational level. So that means in a single or in an electronic transition, vibrational, or I should say during this electronic transition happens. So during an electronic transition, vibrational and rotational changes, energy changes can also. So this vibrational energy, so, so this vibrational change in vibrational energy level, which is called as vibrational core structure, called as vibrational core structure, and this rotational energy changes because of electron transition, which is called as rotational rotational fine structure. So in a single electronic level, we have large number of vibrational levels, and in both those vibration level, we have large number of vibrational levels. So a change in electronic level means that a change in vibrational energy level also. Similarly, when we are having change in vibrational energy, we have a change in rotational energy. So because of this electronic transition, we have a change in vibrational energy level, and that change is called as vibrational core structure. And because of that same electronic transition, when vibrational energy level is going to change, you have a rotational energy level which is also changing. And that change in the rotational energy levels because of the electronic transition is also called as rotational fine structure. And this one electronic energy level that if you are considering the suppression of those energy levels, so that will be 10 raised to 6 centimeters. So it is very large energy difference. So this is the suppression between electronic. So this is just that or which is greater than this, equal to or greater than 10 raised to 6 centimeters. So that difference is larger as compared to the vibrational and rotational. If you consider the energy level difference of those transitions from first energy level to the next energy level. So the electronic transition will be having very large energy as compared to the other vibration and rotational. Which means that the energy difference between the adjacent or the electronic transition difference in the energy levels, consider the electronic energy levels, which will be larger as compared to the vibrational. Okay. So as we discussed earlier, and this electronic spectra does not having any such kind of requirement as which is needed for vibrational spectroscopy and rotational spectroscopy or Raman spectroscopy. So this electronic spectra, which is available from all the molecules. In other words, we can say all molecules shows electronic spectra. All molecules, whether it is centrosymmetric, whether it is homonuclear, or any diatomic single bonded, double bonded, does not matter. All molecules shows electronic spectrum. All molecules shows electronic. So it is a very good idea to use this electronic spectroscopy instead of the vibrational and rotational spectrum, so that we can get the information what we are also getting from all other spectroscopic techniques. But the problem is that we have to thoroughly study or observe the electronic spectra, and we have to analyze that very carefully to get different, for example, rotation constant, vibration that we can derive from these electronics that is given. So since all these molecules which are showing this electronic spectra, we can deduce information from that spectrum corresponding to the rotation constant, vibration, all those parameters we can derive from the electronic spectra also. Okay? And because of all these molecules shows the electronic spectra, it does not matter whether the molecule that you are having that in your sample, whether it is centrosymmetric, whether it is homonuclear, it does not matter. Anyway, you'll get this spectrum. So that is the advantage of the electronic spectra, because all the molecules will show the spectra. So we do not have any such kind of condition like molecule should process dipole moment or change in polarization. Those things are not required. Here we only require that the transition, electronic transition, that electronic transition, and that is obviously will be there for all this. Now we discuss about the vibrational coil structure, which means that the changes of the vibrational levels because of the electronic transition. So first we have to consider the total energy, as we discussed for the case of electronic transition. We also will be having the vibrational transition. Also, along with the vibration, we have the rotational transition. So the total energy includes the electronic transition energy associated with the electronic transition, energy associated with vibrational transition, energy associated with the rotational transition. So total energy, we will write it as if we are considering E total, which will be equal to E electronic transition plus energy associated with vibrational transition plus energy associated with rotational transition. But in this case, we are considering vibrational core structure, so we do not consider this rotational energy for time being. We are discussing the vibrational core structure, so we are only discussing the vibrational changes because of the electron. So the E total. So in this case, we are dropping that rotational uh, energy term. Okay. So E total will be nothing but total energy. Total energy. So total energy without rotational term. So E total will be equal to E electronic plus E, and this will be equal to E electronic plus what is EV or E, I mean, epsilon V. Okay. So epsilon V, that will be equal to V plus half into mu E bar first one. Then minus V plus half square mu E bar XC. Then plus half cube to bar YE plus X. So this much of centimeter. This is the energy. This we already discussed for the case of vibrational spectrum. So this is the fundamental one, that is without any anharmonicity. Okay. When you are having that anharmonicity, then we have the other terms. Okay, so this is the total energy without that vibration, sorry, rotational energy term. And as we know, this we can take values from 0, 1, 2. So these are vibrational. Now, if you consider this electronic transition at this stage, then we have to look to this diagram. this one. So this first diagram you can see this one. So these are the electronic energy levels. E double dash EL, E dash EL. Okay, here we have L dash. Here we have L double dash. And this is an obvious notation that we are usually doing in this course, that dash is for the excited or the higher energy, and double dash is for the ground. Okay, so the transition that we label here, as you can see, so this is EAL dash, which is the higher energy level of the higher energy electronic level, okay, electronic energy level. And within that electronic energy level, we have different vibration energy levels. You can see 5x. Here also we can see 0, 1, 5. So within a single energy electronic energy level, we have different number of vibration, and we have also denoted this V vibration energy level as V dash here. Dash. This is V double dash because the lower energy level is associated with vibration energy V double dash, and the higher energy associated with the vibration. And the transition also, if you have transitions, you can see that these transitions are denoted as lines. Okay? So this transition which is happening from this 0, ground state is 0, stated state is also. So this transition is denoted as, so it is just like V dash comma. The next one is 1 0 transition line. Okay. Dash is 1. Clearly, you can observe all those lines where we have the dash. So this is a representation of rational from the ground state. So this is only the case for the ground state. Then you can consider this one state transition. So then it will become very complicated. That is not included. Only this ground state we have. We can also have the different transition state. One, the double dash also can. So we will be having large number of transitions. Any transition which are possible, we do not have any correction. So any transition that is possible with structure, sorry, vibration of structure of the absorption. So here all those transitions are possible, but we have shown here only the. So as the excited state electronic state corresponds to weaker bond is unstable. Okay. So that the vibrational levels in the excited space, it's weaker. So this here we will be having more close. so that you can observe here, show all the lines here. Now, if you consider the new bar, that is the frequency in limiter inverse, that will be given by the difference between energy level. That is what we are doing. The mu bar is nothing but the difference between the energy level. So it is just like it's new is the energy difference between the energy. Then you can have bar which is equal to epsilon electronic dash epsilon electronic energy level difference between electronic energy separation between, and then we have plus we have the other term which is associated with pressure. So we can consider first half. Okay, and here we will be having the dash because we are considering first plus plus here. So in this case, we are not considering first meter state. Okay. And in the ground state, so if you consider ground state, we will be having terms with double dash. Cannot consider that. So then we have to abstract this particular term. Have to subtract. That's a subtract. Where dash. So this is basically this is different. These two bracket terms which is in this side corresponding to the energy. The difference between the energy level, vibrational energy. These two terms represent, and this term representing the chronic data angle. That will give you the bar that is corresponding to the number along with the vibrational code. So this is the frequency or the wave number that you can observe correspondingly So as we discussed, any transition has some video. We do not have any such having so 5 years no such kind of selection. Here also all the transitions are probable. But the more intensity will be uh, spectral line arising starting from V double dash equal to 0. So, and in the ground state we have V double dash equal to 0, and from that if we are having then that will be more intense. I'm not going to write all those points here. Just more intensity will be intensity. More intensity will be corresponding to the transition. So we have V double. So these lines will be or this transition more intense. So any transition are probable as I discussed in direction. Any transition that are probable. So, but the more intense line will be corresponding 0, 0, 1, 0, 2, 0, more intense as compared. And the set of lines corresponding to these positions. So that those set of lines which is corresponding to this particular transit, which are called as progression. Called as progression. Hence the value of mu dash increases. These lines transition progression as why it is called as progression because v dash increased by for each line the v dash value you can observe from here dash is equal to dash equal to with the constant v double dash dash is here. Okay? And such lines of all such lines can be progression. And if you consider wave number corresponding to the 0, 0 transition, 0, 0 transition, 0, 0 transition, this will powerful. This is simply substitute b equal to both b dash equal to 0, dash equal to b dash equal to then that's then minus plus value. Then minus minus will get plus c double dash. So this is the wave number corresponds to the equal 0 b dash equal to 0. So observation of few lines in a band that enables one to determine the and also so all those constants. So in this case also we need observe we have to observe some few lines. So actually this will give you a band structure because this will be giving you some that energy will be shifted in terms. So a band will be observed and analyzing the lines in that particular band. All those things we can get from after analyzing. Now we will consider the vibrational analysis of the band. Vibrational of band system is this can be labeled band as so vibrational term value is vibrational term that can be given by this epsilon of or you can write epsilon b itself. So write epsilon. So epsilon b will be equal to a plus half r square. that is the vibrational term value. So in vibrational analysis, we are so in vibrational analysis, E equal to 0. So this particular energy level which we called as 0, it's 0, zero level. So this particular energy level V equal to 0 is called as 0 in vibrational. Okay. So the modified system vibrational will become, if you consider that energy of the vehicle that will be equal to half. So this is nothing but half the bar. We just substitute V equal to 0. Then we'll get half bar, then minus by 4 bar plus 1 by 8. So this is the energy in centimeter inverse for the case of zero. So here I just substitute, for example, that substitute V equal. So here this modified term, this is your, so the modified vibrational term can be written as just writing this uh, so after including this modified vibrational term, that will modified zero. Right, modified. Just expanding. They are not considered. So all other excited state also will be. Then this is just an expansion of this this expansion. You just expand the starting the then minus half square. So we have 9. Then we get now you can take all these. Plus etc. There may be other and then we have the next one which is v squared. So minus v squared times plus etc. Also have third one plus term plus also plus. So this we can simplify as e. And I just put this as 0 bar. Then second term I will put as 0, 0, 0 bar. The third term y0. So we can 5 times 0 then plus 4 plus etc. What I have done here that 0 bar. Then this particular brand term in bracket so into For that this is x0 into okay. So in the modified form, okay, so this is the how do I how we have the form modified form. Wave number of so I'm about this EV in the transition transfer transition then give that spectral line. So that spectral line will be so just subtract from the next so if you subtract that, plus p dash dash where we use the number of so this is this is the expression for the wave number that this